All right, great. Well, good morning, everyone. My name is Oses. I'm a postdoc at Duke University in the Center for Autonomous Materials Design, and this is the last session for the morning, and then the last session for the AFLOW section here of this workshop. And we're going to wrap up with a really nice topic. We're going to talk about the AFLOW machine learning module, which combines our materials database with machine learning. Okay, so we talked about the AFLOW database extensively, the size, how we populate it with different structures and different elements. And we talked about tools like the REST and search APIs, AFLUX, the last session, about how to wrangle that data. But there's a big problem. Despite that we have a very large database, there's a lot of materials that we've yet to explore. And running these sort of calculations to model these materials requires density functional theory, and this requires a tremendous amount of resources, a lot of time to do these calculations, and any individual calculation can take days to months. And so what we want to do is we want to be able to leverage the existing data that we have to make predictions on new data that we haven't calculated yet. And so we're going to be talking about constructing models that can predict properties of materials, understand some of the trends and relationships among properties, and even understand relationships among materials. Okay. So I'm going to talk about a particular study that we did back in 2017. It was published in Nature Communications. This is where we constructed what we call the property label materials fragments. We took the AFLOW data, some of the data that we've been using in this workshop. We took the data for about 30,000 materials, and we trained the gradient boosting decision trees machine learning model. And so there's a whole zoo of different algorithms that you can use for machine learning modeling. What I want to emphasize is that the most important piece of modeling is figuring out how to represent your material, your crystal, in a way that the machine learning algorithm can understand. Assuming that you can represent the crystal or the material in a machine readable fashion, and you have the right properties of the material to train on, the algorithm is not so important. You might be able to squeeze out additional accuracy with different models. Some models do better than others, or faster to train on. They can train on fewer materials, but in general, I want to focus on constructing the representation for the material. So how do we represent? In our case, we have a database full of crystals. How do we represent a crystal in a way that the machine learning algorithm can understand? So with a crystal, we're going to have a periodic arrangement of atoms. Here we have a small subsection of that. We have an atom here in the middle, the center, and we have some nearest neighbors that we're showing. We're going to model this material fundamentally as a graph network. Okay, so we're going to represent the atoms as nodes and the bonds as connections. And the way that we do that is we analyze connectivity in the crystal by doing Voronoi tessellation. Okay, so if two atoms are bonded, then they're going to be within a certain distance of each other, and they're going to share a face here from the Voronoi tessellation algorithm. Let me get the chat up just in case some questions come up. Aside. Okay. Oh, by the way, I'm going to share my slides and the Collab notebook for the next part. I just shared it in the chat, so you can click on the links. You can follow along with me on the video, and then you'll open up the Collab a little later in the talk. Okay, so we need the Voronoi tessellation algorithm, and we need to check for distances between atoms. Using the combination of the two, then we can establish connectivity within the material. So now that we've represented our material as a graph, we have our atoms as nodes, we have our bonds as edges. we can actually represent the material in this fashion, and we can build up what are called fragment descriptors. So we can look at adjacent joined connections in the graph. So we have what's called path fragments. So these are just linear connected atoms of a particular length size. And then we can have circular fragments, and this will model a coordination sphere in the material, nearest neighbors. And so what we do is that we build up a long vector of statistical properties based on these fragments. I'll give you an example. So we decorate the nodes here with the properties of the atoms that they represent. So here we have, as an example, we have atom type 1, we have another of that atom type, and here we have atom type 2. Okay, so we look at the individual properties of those atom types. Let's say we look at valence electrons or ionization potential. So if we look at this path fragment, we'll take the average of the ionization potentials of the atoms in this path fragment. So we'll add up the ionization potential for this atom, and this atom. We'll take an average, and that's going to represent one entry of a very long vector that's going to be, think of it as like a fingerprint of that material. Okay, so we're going to build up these very long vectors that are represented, that are going to be statistical properties of all of these elements, standard deviation, average, the difference, all across different path fragments in the material that we're representing. That's going to constitute this properly labeled materials fragment. Okay, and so that with that one construction, we were able to build a number of machine learning models. Okay, so the first two I'll talk about. The first one is a classification model, and so we're interested in understanding whether the material is a metal or an insulator. And we built another model on top of that where if it is predicted to be an insulator, then we predict the band gap, and that's a regression model. So here we have the results for that model. We trained on the material, the band gap that's calculated with DFT plus U calculations. So we correct a bit for the band gap. We have a plot here of the calculated band gap. So these are the results that we get from density functional theory, and we compare it to the predicted values from our model. This is based on a 5-fold cross validation. And here we have the results. You see that the root mean square error is about half of an EV. The mean absolute error is about 0.35 EV, and R squared is 0.9. So the model's working very well. We, using this exact same construction, the PLMF model, we built a number of models. So here again, we show the electronic properties, metal versus insulator. That's a classification model. If it has the band gap, then we can predict that with another regression, with a regression model for the band gap. And then we also built models to predict the thermomechanical properties. Okay, so this includes bulk and shear modulus, the Debye temperature, the heat capacity. So we built a number of regression models to predict the thermomechanical properties. What I want to point out is that to train the electronic properties models, we had about 23,000 compounds. And for the thermomechanical properties, we had about 3,000 compounds in our database. Now, the discrepancy between the two has to do with the fact that it is much more difficult and expensive to calculate thermomechanical properties. So if our calculation for electronic properties is 1 unit of calculation, thermomechanical properties can be a factor of 10 to 20 times more expensive to calculate. So that means that these properties are much more difficult to get at, and that actually makes these machine learning models that much more useful because we can save time, we can pre-screen and look for materials that have interesting properties using these models. So the next question is, now that we've built these models, we want to understand, did the machine learning algorithm pick up trends that we understand and we know should be true about these properties even between properties. So one way to analyze whether the machine learning algorithm actually understood some of the underlying physics of the problem is we can plot these partial dependence plots. So here we look at the relationship of the bulk modulus with the volume of the crystal, and you can see that as the volume increases, the bulk modulus is going to as the volume increases, the bulk modulus goes down. And so what that means is that the material is getting, if the material gets smaller, we're going to have a higher bulk modulus, and that means it's basically associated with the bond strength. Because if the atoms are closer together, then we understand that the bonds are stronger. So we see that it picks up on that trend, that if the bulk modulus is very high, then you're probably going to have very strong bonds. Another relationship we have is we look at the Debye temperature, how the Debye temperature changes as a function of the lattice parameters B and C in the crystal. There's two trends to pick up here. As we increase uniformly the size, if we expand the volume uniformly of the crystal, the Debye temperature is going to go down. However, if we increase one lattice parameter with respect to the other, we elongate the crystal, then we have a way of really increasing the Debye temperature. The Debye temperature is very closely associated with the phonon properties of the material, and so it's well known that by creating layered materials or introducing anisotropy in the material, we can actually increase some of these phonon phenomena like thermal properties, superconductivity, and the like. So this model is picking up on that. I have a question here. What is the computing cost to calculate ionic transport? I'm actually not an expert on calculating ionic transport. I don't know if any of the others want to comment on that, but I don't know the expense of calculating ionic transport. Okay, so for now, I show here we show a three-way agreement between the experimental values, calculated values from the AFLOW database, and then predicted values from our machine learning model. And we show them here for bulk and shear modulus. You can see that there's a very nice fit, that not only modeling well to DFT, the DFT predictions, but we're also modeling very well with experiments. So the three are aligned. And that's ultimately what we're looking for. So we get an R squared here for bulk modulus of 0.99, is very high, and R squared of 0.97. So the models are working very well. Okay, I'm going to stop sharing my screen. I'm going to show you. We're gonna head to the AFLOW website, and we're gonna work with this machine learning module through our online website. So stop sharing. Okay, and then I'm gonna go ahead and share my screen, my full screen. Desktop one. Okay. Should be able to see my web browser here. We recommend that you use Firefox. I think we discussed that earlier. But what we want to do is we want to go to aflow.org. I'll blow up the size here once I get on. Okay. So now that we have the website, full screen as much as possible, we're going to scroll down. And we're going to go to the AFLOW-ML Online portal. I'm going to click on that. Okay. So here we have our online portal for a machine learning app. Just the other side. Okay, so here's the full page. We actually have a nice set of instructions here, but you can just follow along with me on the screen. So first, you're going to want to select the model. So I talked extensively about the property labeled materials fragment model. So it's one of the models here. We have a reference for it. We have 3 models in total that you can use for predicting properties of materials. We have what's called the molar fragment descriptor. This is going to model some of the vibrational properties of the material. And then we have the AFLOW superconductivity model, which we worked with Professor Takeuchi and Valentin Stanov. We have the link here, but this will predict the superconducting critical temperature. Okay, so let's go to the PLMF model. We're going to scroll down, and as a default, we actually have what you can do is you can provide a structure. Okay, and so here we have just an example structure from the database. You're going to see that an important note to make about the structure is that it's in the VAST postcard format, and it's VAST postcard 5. So we need to provide the species here as an input. We need to tell it that there's chromium and silicon in this material. Okay, so you don't have to do anything, just hit run prediction, and you should see a little card pop up at the bottom here in the predictions, and it's going to run for a few seconds. This is actually going to our server. It's going to perform the calculation, and it's going to return back the results in a few seconds. And so you can see here that very quickly we get back the result. You see that it's predicted to be an insulator. We get the band gap, the energy of this per cell, or the energy of the cell. We get bulk shear modulus, the heat capacity, constant pressure, constant volume per cell and per atom. We get the Debye temperature and the thermal expansion. And then we have some calculation details. These are just calculation details that AFLOW takes as a standard, in case you want to know how these properties were trained. Because of course, if we train with slightly different parameters, we might get slightly different results. So these are just some important details about our calculations. Let me make sure that I have the chat up. Okay, so I just want to emphasize, this took a few seconds to run, much faster than what you would expect to do with density functional theory, especially for these thermomechanical properties that are very expensive to get at. Okay, let me pull up the slides again. Okay, so I covered the model. I talked about the difference. Okay, so there's the VAST4 format here. This is the usual format that you might find in AFLOW, and then the VAST5 format here contains an additional line with the species. Okay, so you see the species here, and then you're going to see them. You should put them over here, and then the model is going to understand the species and the structure. I will get to your question in 1 second. I want to take a moment just to explain the exercises, and then I'll cover your question. But we'll take a few minutes. Let's see, yeah, we're on time. We'll take a few minutes to go through a few exercises. We'll take 5 minutes to do so, but let me just walk you through the exercises. You're going to want to use the AFLOW prototype encyclopedia to look for the Heusler structure. Okay, it's a ternary. And the default should give you aluminum, copper, manganese. And you're going to want to take that structure and convert it to a VAST5 postcard. You can actually do that inside of the prototype encyclopedia. You're going to want to copy that structure into the AFLOW-ML application and then run it using the PLMF model. I give you some questions here. Is it a metal or insulator? What are the values of the bulk and shear modulus? That should be pretty easy to pick out. Run the MFD model, see what kind of properties you get. And then you're going to want to take the chemical formula and see if you can plug it into the superconductivity model and see what is the critical temperature you get for it. All right, so we'll take 5 minutes to do that. And while you guys are running that, I'll look at the questions we have in the chat. Let's see. So we have, are these property values calculated from ML model or from actual DFT calculations? They are, okay, the model was built on density functional theory calculations. If they are from ML model, what model is the accuracy R squared? Yeah, I gave some of I gave some of the accuracies in the R squared values for these models in the slides. But I will share with you the publication, and you can actually you can read a little bit more about the accuracy there. Can you comment once again, please, what you do for lithium-ion batteries and how your toolbox can be applied to energy materials in general? Can it be used for electrolyte systems or for the systems electrolyte? There's nothing specific about whether we certainly model crystal materials. That's kind of our niche. But aside from that, we tend to focus on metals. But there's nothing to say specifically that that we work on any particular chemistry. Okay, so AFLOW can be used to study anything that you might work on, in particular with density functional theory. For lithium-ion batteries, if you're interested, and if it's something you can represent in a crystal, you can actually use the AFLOW-ML module to predict some of the properties that we have here. So if you have a particular structure, you can go ahead and take that structure, plug it into our input here, just as I've done on the website, and you can model these materials right there from the web page, the web portal.
But you have many lithium-containing compounds in the database, right?
So Cormac touched on this a little earlier. We definitely have lithium-containing compounds in the database, especially from the ICSD. So and these were included in training these models. I wouldn't say that we specialize in lithium-containing materials. We don't have a particular focus on batteries, but some of these materials that are used in batteries are contained in the database. And so if you're interested in understanding what's sort of contained in our database, you can actually construct some of these queries with the AFLUX commands that Marco gave you earlier. You can search for materials containing lithium, and you can get a certain count on that. You can focus in on those materials. You can plug, if you're interested in seeing what the model predicts for those materials, you can take the postcard and plug it into the module here and run it. So, but to that extent, I think it's not a particular focus of ours, but we do have lithium-containing materials in the database. Does ML material property predictor work well across various classes of materials, metals and semiconductors, and chemistry, say oxides, nitrides, semiconductors, or is it only good for a specific class? So I would say that we certainly didn't limit it to metals or semiconductors, right? We have both types in our database, and we constructed a model so we can predict metals versus insulators to a very high degree. And in terms of chemistries, we have oxides, we have nitrides in the database, and so we certainly have we go across all of those chemistries. Again, as Cormac said earlier, I would say that our particular focus as a database is generally on intermetallics and metals. We have a lot of those in the database, but we certainly have insulators in the database. Okay. There's a link for the website.
Corey, please unmute it again. I had to mute everybody. So.
Okay, can you hear me? Okay, great. All right. Can any of your ML models or DFT calculations predict crystal phase transitions, for example, at high temperatures? Yeah. So I think I posted the link earlier for Marco or Cormac. If you can grab the link for the LTVC paper, but well, that's for predicting the order-disorder transitions. There aren't any particular models for specifically predicting the temperatures of crystal phase transitions. We don't have a model on that. But for order-disorder, we do have a model for that, and Cormac can post that in there. Okay. All right. Perfect. Can we save the output predictions in AFLOW-ML? I'm gonna just after we go through the exercises, I'm going to show you how you can do this programmatically, so you can actually save the results in files. You can do this. We can write some code. We give you some Python scripts, but you can actually run this programmatically. That'll be the next section of this. Okay, let's go through the exercises. I'm going to make this a little smaller so that I can put both of them side by side. Okay, increase it a little bit. Okay, so all right, so let's go to aflow.org. In a second, we're going to go down to our prototype encyclopedia. I think the easiest way to do this is just to type in Heusler. And you'll see that some results come up for the half Heusler. You really want the full Heusler structure, which is the second one here. Okay, so you see that we pulled the right one because we have the right chemistry. We have aluminum, copper, manganese. Okay, so we scroll down. We can actually create the structure just from the default parameters given here. And you see that we get the VAST postcard 4 format. So I'm going to quickly create the VAST postcard 5 format. So we give the unique species here, aluminum, copper, manganese. I'm going to copy that. And I'm going to go back to the web page for AFLOW-ML. And I'm going to just copy, paste it here, run prediction. You see that we predict that it's a metal, and we have the bulk and shear modulus values here. Okay. We can take the same, we can just having the same input. I think it's going to change it, but I'm just going to delete this here, paste it again, and we're going to see what the MFD model gives you. It's much faster, and you can get the vibrational properties for this material. So we can get the heat capacity per atom, the vibrational free energy, and the vibrational entropy. Okay, and we get the values here. And then as for the last one's interesting. It's a little bit of a different input. You want to provide the composition. So we had, sorry, let me just, because I don't see it here. We had, we basically have aluminum, copper 2, manganese. So that's the composition. So aluminum, copper 2, manganese. And we hit run prediction. This one takes a little longer to run. There's a lot of features that it needs to pull out and model. But if you give it a few seconds, you'll see that we actually have two prediction values here. Basically, without going into too much detail in the study, I can provide the links for the publication a little later. But when we were modeling these systems, when we looked at the data sets, there were a lot of materials that had very low TCs and a lot of materials that had high TCs. And so we actually partitioned the two sets, and we created a threshold temperature above which we characterize high TC and low TC. And so based on what that transition temperature is, it's going to affect the values of our predictions for the transition temperature. We show them here for two different separation threshold temperatures, one at 5K and one at 10K. But basically, you can see here that it's basically not predicted to be a superconducting material. Okay, so those are the exercises we get here. Looks like we had some questions. Okay. All right, looks like they've been answered. Okay, does that mean that AFLOW superconductor does not know about the structure and only about the composition? That's correct. That is correct. So it works basically, it builds features that are based on the composition. Okay, so, all right, so let's go.
Missing still.
Sorry?
There's a question by Lejean. It's a little longer.
Okay. I guess the ML workflow is engineer some features according to some physics theory like bond length angles. We extract some features on the structure, yes, depending on the model. Some models are compositional based, some incorporate features of the structure like the PLMF model. Get data from AFLOW database and transform the data set. Exactly. Train regression classification models. That's right. Evaluate the model with the test set. That's right. The model is good and generic. Then it can. Yes, that's right. That's exactly right. And that's those. And these models that we have here have gone through that workflow. Okay. How did you get the search? So I did that by going to. I'll show you real quick again. So if you go to AFLOW.org. David talked a little bit about the encyclopedia, but if you go here to the prototype encyclopedia, you click on that button and you type in Heusler and you hit search, okay? And the particular material for our example was this second one, the full Heusler, okay? All right, let me pick up with the slides again, assuming that we've gotten all the questions answered.
And just to add to Lee's question, yes, you can of course use AFLOWs to get all your features and run your own machine learning model on the data if our models are not what you're looking for. So
sure. Yeah, I think Cormac's gonna if Cormac or Marco, if you could send the links out. I guess if you could do it for the 3 models, they should actually if you don't have, if you actually look on the AFLOW-ML, you actually see the references here. So if you want to know more about the superconducting model, this is the link for it. It'll describe all of these details about the different thresholds that we had, which really is an artifact of the data set we modeled with. And then we have all the details for the MFD model here, and then the PLMF models, all of those details are here.
I think Jessica has a good request to compile the references that we have into just a document.
Into the canvas. Yeah, we can work on that. We can do that over lunch. Yeah, for sure, we can do that.
Yep.
All right, I'm gonna just take a few more minutes to go through the rest of these slides. Let me pick up. Let me see if this works. Can you guys see the PowerPoint here? Yeah. Okay. Great. All right, so the last piece of this, we've really gone through a lot of the details of how these machine learning models work. I just want to talk about another way that you can interact with the module, and that's through our API. So we talked about how to play with the models on the web portal, okay? But you can actually you can actually do this in a programmatic way. You don't have to copy and paste things into a web page. You can actually programmatically, if you have the files on your computer, you can actually submit queries through your computer to our server directly and get back the results in a format that you can use in a code. So, and actually this is how the website works. It actually makes these requests in the background using the API. So there's a programmatic interface. It's a simple interface. Part of the power of this is that you don't need to install anything. You don't need to know, you don't really need to have a full in-depth knowledge of how the machine learning algorithm is working, what the libraries are. All of these details have been obfuscated almost in the form of a black box. You basically submit a structure with a particular chemistry and you return back the properties of interest. And all of those details of how the model worked and all that have been sort of obfuscated. And it also serves as a centralized location to update the models as our database grows. So how does it work? It's pretty simple. You take a structure in the form of a file and you post it to a URL endpoint. Okay, and so that URL endpoint, the key part of it is going to have the model here. So it's going to be PLMF, MFD, or ASC for the three models that we talked about, / prediction. Don't worry about these details. I just want you to have the big blueprint in your head of what we're doing. So we're going to post it to a particular URL, and that URL is going to respond back with an ID. And basically what it is you can imagine that imagine if you're going to go take out food. Okay, so you submit your request, they give you back a number, and you wait for your order to be fulfilled. So you get back a number, that's going to be your task ID, and then you wait in the line for your food to be ready. And you basically do that by querying another endpoint for your results. So prediction results ID. If you query that endpoint, you're going to get back a status. It's going to tell you pending, or it's going to tell you successful. Okay, and so once it's successful, it'll return back all of the properties to you once that status is successful. So just keep in mind this idea of ordering takeout food. You go in, you put your request, you get back a number, and then you wait until your number is called, and then you get back the prediction. So what does this mean? Oh, by the way, if you guys are Python people and you like working with Python, you can actually download a client that we've created, which integrates all of the code that I'm about to show you in a very easy way. If you go to aflow.org /source/AFLOW-ML, you can actually get this client, and it has all of these scripts that I'm about to tell you that you can run in an easy way through the Python interface. Okay, so what do these commands look like practically speaking? If you're familiar with webget or curl, this is the command you're going to do. So this is going to be posting our postcar file to this endpoint. Remember, I talked about the endpoint being the model and prediction. Okay, so you're going to post your postcard to the server. You're going to say, this is the order I want. It's going to return you back with a number, basically what order, an ID. And that's going to be basically the number you're going to request and say, is my order fulfilled? Is my order fulfilled? So you take that ID, You're going to do another CURL command to the endpoint prediction result, and you're going to plug in that ID. Once your results is fulfilled, you're going to see status equals successful, and you get all of the properties that you can get from that model. Okay, so we get the bulk, shear modulus, the electronic band gap, all of the properties we talked about earlier. Here's a Python script that we provide to you. It's actually going to be in the Collab that I posted the link for earlier. But let me just highlight some of the features here of the script. We have the server, the API, and the model here. Okay, so you can easily change out PLMF for MFD or ASC. And then you have the postcard here. This is the file that you want to submit to that URL. And this code here takes care of submitting the structure and then getting back the ID. And so basically, while the status is not successful, it's going to run a while loop, and it's going to keep querying: is my order fulfilled? Is my order being fulfilled? Once you see status equals successful, it's going to print out successful prediction. It's going to print out all of the properties that you get from that result, and then it's going to break out of that while loop. All right, so we're not going to have lunch. We're going to wrap up for lunch in a few minutes. I'm just going to show you the Collab that I gave you. I'm going to post this link again in the chat because it's moved up. Oh, great! I'm happy you like the analogy. So let me make the font a little bigger. Okay, so if you just click on that, what I'm going to ask is you definitely should create a copy in your drive. Open new tab. Okay, so now you have your own copy. You can play with this as much as you want. Here we have some of these details that I talked about earlier. So this is going to talk about the API structure, the posting, how to get your order number, and then how to query back the results. So here we have the image. It gives you the full set of what you can expect for every step of that query process. We talk a little bit about the models that you can use. So here we have some information from this paper. We have the article here that you can go in and look at that article there for the PLMF model and for the MFD model. So you can use the API. Here's the CURL example. So here we have our test postcard. If you just run this, you're going to see that it's going to grab a test postcard from our database, and it's going to print out that test postcard for you. So it's going to kind of save that in this notebook for you, and you can see that it's in the VAST postcard 5 format. This is the same example we used in the web portal. You can run this example. So it's going to take that test postcard and it's going to post it for a prediction. So again, we're just kind of running through each step individually. We get our order number. Okay, so we take this order number here, our ID. We're going to copy that and we're going to paste it to the new URL. So that's going to be our new query, but without the quotes. Okay, we're going to hit submit. And because there's been a bit of time, there's not a lot of, you can imagine there's not a very long line waiting for your takeout food. The request has already been fulfilled. So we get status equals successful, and we get all the properties that we asked for. Okay. And then this is the Python script that I provided you earlier. Okay, so you can just hit run. You don't have to worry about anything. You just hit run here, and this gives you back the result. This URL here for the query. You can take that. You can copy it. And in the next piece, you're going to want to paste it into the results URL, and then it's going to walk through that process of querying and saying, has my order been fulfilled? Has my order been fulfilled? And if it has, it's going to print out the results here. Okay, and then we provide the full script as one piece with the while loop, so you don't have to worry about walking through it step by step. So I give you an exercise. You can complete this in during lunch. And if you have any questions, we'll be around to answer it. We'll also give you our emails if you wanna post a question. But basically, I give you another structure. You can take that structure and you can copy the Python scripts from the scripts above, and you can run the Python script to get back that individual query. And so I'll just make a note that you can basically just want to copy this code here, this whole code, put it in the next cell. You're going to want to change the name of the postcard because this is going to save it as this file here. It's going to be called MGO rock salt postcard. So instead of test postcard, you're going to copy in MGO rock salt postcard. Then you're going to copy the rest of that Python script, run it, and you should get predictions for all of your models. Okay. And I give you some space to do that and work with it. So unless there are any questions, let me see. So there's, in general, how frequently should we query to see if our jobs are finished? So in the, I didn't talk about it, but basically there's a sleep here. So sleep 10 seconds. So if there's a lot, let's say that it's a particular time of the day, because there's some times in the day where we get heavier with more requests. You should query every 5 to 10 seconds for whether the result has been finished. So in the script, it automatically is going to wait 10 seconds for you to do that. So it's going to go through that while loop. If it hasn't been completed, it's going to wait 10 seconds, go again, and then you should have the result then. I would say no more than 2 or 3 steps, and it's going to be finished there. So yeah, 10 seconds. Any other questions? Yeah, we have our emails here. Marco, thank you very much for providing them. Marco, you have a summary slide, right?
I have the summary slide. I'll do the summary.
Cormac. Okay, great. So I will, if that's okay, I'm going to wrap up here. I'm going to stop sharing. Thank you very much for your time and attention. And if you have any questions, feel free to email all of us. So I'll pass it over to Cormac now.
Okay, nice, Corey. Let me share my screen.
One quick question, Corey.
What was the placeholder to paste in the URL? Yeah, let me paste what that answer looks like. So in the, it's basically the result of that one cell. It's going to print out, and you're going to want to do it as a string. So it should look something like this. This is my individual query. You're going to get a different ID because basically you're just another order in line. You're going to get a different ID. This is your query. This is your order number for that takeout order.
Thank you. Yeah, the question should have been more specific. In the Collab, where do I input that? I missed that.
Let me, Cormac, if it's okay, I'm just going to share a screen real quick. Basically, second, it's going to be right here. Okay, so take this. And you should have the results URL, and before it was I believe it was a diamond. Yeah, you're gonna get results URL. So you just take that result here, copy and paste it as a string right there.
Got it. Thank you.
No problem.